Hello everyone and welcome back. In this video we're going to continue looking at exponential functions, but we're going to look at something called continuous growth versus being compounded quarterly, annually, monthly, or other types of growth. In the first slide, hopefully you've seen, if you've opened the notes already, that we are looking at some review problems for graphing exponential functions. So at this point, I would ask if you pause the video and try to graph those two functions. Come back when you are done. All right, hopefully this is what you came up with when graphing those functions. Let's move forward with our look into compounded interest. All right, so these are some exponential growth and decay interest formulas. Now the first two, growth and decay, they're the same formula. The only difference is one is growth, one is decay, so it's plus a positive R or a negative R for decay. The next one, compounded interest, that would be if our interest is being compounded daily, weekly, monthly, quarterly, biannually, whatever. Okay? And the last one, we'll talk about this more at the end here, if it's being compounded continuously. Now, you are not probably going to find any banks that give you interest that compound continuously, but that formula is very important for other things that do grow continuously or decay continuously, such as any carbon-based compound or bacteria. Let's just go through all the letters here and see what they all stand for. Capital A is the final amount in the account. Capital P is the principal, which is the original amount invested. R is clearly your rate for the year. We want to make sure that if that rate is given as a percent, we change that to a decimal by moving it over 2 spots to the left. N is the number of times compounded each year. So if it's yearly, that N is 1. If it's monthly, that N is 12, so forth and so on. And then T would be your time, and that's always in years unless the problem states differently. All right, we will need a calculator for almost all these problems now and in the future. So if you need to get a calculator out right now, go ahead and pause the video and do that. Otherwise, we're going to move on to take a look at these 5 problems right here. Okay, that's the same problem, just that we're going to switch up how the interest is being compounded. So the problem reads, upon graduation from Glenbard North, you receive an inheritance of $10,000 from a rich relative you do not even know existed. The money has been placed in a certificate of deposit which earns 6% interest compounded annually. Now at the time of this video, 6% would be an outstanding rate. Most of the rates right now that you can get are somewhere between 3 and 4%. So if you can get 6%, that would be a really good place to put our money. The question says, what is the value of the certificate after 6 years? All right, so let's just read through this question again, and we are going to kind of figure out which equation we're going to use and plug these numbers into the spots where they belong and figure out our answer. All right, so we received an inheritance of $10,000. That's going to be our initial amount. The money's been placed in the CD, which earns 6% compounded annually. So that would be 0.06 for R. And then the value of the certificate after 6 years, 6 would be our T. All right, now because this is compounded annually, we have a choice here of 2 that would actually work. This one or this one. Okay, why would either one work? Well, if we chose this one, and since it's annually, that means N is 1. So really, this would just go away, and we don't really need this either. And then that formula turns into the same formula that we have here. So I'm just going to use the growth formula, which is P times 1 plus R to the T. All right, so our A equals our principal amount, which is 10,000, times 1 plus R, which is 1 plus 0.06, to the time, which is also 6. And that's our equation. Now we can pick up our calculator and type that in exactly as we see it. And let's see what we get back. I'm getting $14,000, $185.19. So $14,185.19. For money, always, always we round to the nearest penny. All right, now suppose that instead of compounding annually, now we compound quarterly. Quarterly means 4 times a year. What would the value of the CD be at the end of the 6th year? So now we don't have a choice. Now we're going to have to use this formula here. P and R and T are the same. The only difference here now, N, quarterly would be 4. All right, I get A equals 10,000, 1 plus 0.06 over 4 to the 4 times 6. Okay, and that is our equation that can go straight into our calculator at this point. Now, because we're compounding it more often than the first one, we should end up with more money. And we do. We end up with this time with $14,295.03. All right, now suppose the CD is compounded monthly. So now we're compounding even more, which means we should get more money at the end. Monthly means 12 times a year. So we're going to use the same exact formula and simply change the 4s to 12s. All right, so go ahead and pick up your calculator. And again, we're going to do the same thing. We're going to change the 4s that we had to 12s. And after you put that in, you should get back a little bit more money. So $14,320.44. The last ideal here would be the best one, unless it was compounded continuously, but this one's compounded daily, which is a whole lot more than monthly, right? So we're going to use our same exact formula. But change the 12s to how many days are in a year, not counting a leap year here, of 365. Okay, and we can go straight to our calculator at this point, type in 365 for both ends, and we should see that we're going to get more money than the first 3. And we did get a little bit more money than the last one, $14,332.87. All right, the last question here says, what if your parents had deposited some money in a CD when you were born so that the second you graduate, you would have $10,000? Let's assume that you turn 18 when you graduate. How much would they have to deposit, assuming that the interest rate all these years has been 6% compounded annually? So again, it's annually, which means we can use this one or this one. Doesn't really matter which one, because this one's a little bit easier to use. I'm just going to use that one right there. And now we want our A to be 10,000. Okay, so that means we're going to look for P this time. All right, so I want 10,000 to be here. I don't know what P is. My R is still 0.06. And we're going to assume that it's been 18 years. All right, so the first thing we probably want to do is figure out that 1.06 to the 18th power is. I'm getting about 2.854. And then we can divide that 10,000 by that number. And we should get $3,000, almost, $335.03 and 44 cents. Okay, so what that is saying here is if when you were born, your parents put $3,503 into an account that got 6% interest every year, When you graduated, you would get $10,000. We've used all of them except for this one here. That's where our last page is going to come into play. That E is called Euler's number. It's a very important number in a lot of mathematics. If you want to read through here, you're welcome to do so. But basically, we see it a lot in bacteria, population, and radioactive decay. Those are the three main ones that we'll see. Okay, this is continuous growth, meaning an object is constantly being compounded. Okay, the interest is earning interest constantly. Okay, so this mathematician, Leonhard Euler, some people say Euler, some people say Euler, discovered this constant to be this number E. Now, if you take calculus, you'll figure out exactly what that number E is and how he figured it out. But right now, all we need to know is that E is a number, it's approximately 2.7, and it's used in our growth formula. So all the letters mean exactly the same thing. The only difference is E now is in our formula, and E is approximately 2.718. But we don't have to memorize that number because the calculator has an E button on it. Okay? So let's take a look at this one problem we're going to use it for here. The growth rate of the human population is approximately 1.1%. If the world population right now is 7.888 billion, which it is not, but I'm just going to throw a number out there, what would the population be in 5 years? All right, so population grows continuously. It's not annual, it's not monthly, it's not daily, it's continuously growing. All right, so we're going to use this formula right there. All right, we don't know what A is, that's what we're trying to find. The p-value here is 7.888 billion. We're just going to write 7.888 down here. E is E. The rate is 1.1% or 0.011, and our time is 5. All right, and that is what we're going to type into our calculator here. So go ahead and type in exactly what you see, 7.888 e to the 0.011 times 5. And we should get back 8.33399. So we're going to write 8.334. And remember, our answer is in billions here. So 8.334 billion people. All right, that will do it for our lesson today on exponential growth and interest. Thank you very much for watching, and we'll see you again soon.